We're going to look at SI base quantities and SI base units. SI basically stands for International Standard. That means that everyone around the world would agree on these being the base quantities and these being the base units. So base quantities, they're chosen and arbitrarily defined, and they're used as fundamental components to make up other quantities. So these quantities can't be broken down into smaller quantities. SI base units are the equivalent but units wise. So these units are defined in terms of universal constants, and we're going to use these units to make other units. Okay, the first example is distance. So distance is a base quantity and its unit is meters. And then for time, we have seconds. And then for mass, we have kilograms. And then we have electrical current, which has amperes as its base unit. So this is the strange one because a lot of people think charge is more fundamental, but it's not. Current is easier to measure, so we define these as the base quantity here. Then we've got temperature, and that's measured in Kelvin, not degrees Celsius, but Kelvin. And then amount of substance, that's measured in moles. Okay, and then this one you don't really know, luminous intensity, which is measured in candelas. Okay, that last one is not that well used at A-levels. Okay, now that we've looked at the 7 SI base units, let's look at derived units. Okay, so these derived units are made by taking the base units and then multiplying them together or dividing them or raising them to some power. So we're going to look at some SI derived units and we're going to write them in terms of their base units. Yeah, let's start off with coulombs. Okay, so coulombs is the SI derived unit for charge, and the simplest equation I can use is charge equals current times time. Okay, and I'm going to draw a dotted line, and below that I'm going to write in terms of units so that I don't get mixed up between quantities and units. So coulombs is going to equal the unit for current, which is amps, and the unit for time, which is seconds, amps seconds, and that is already in terms of base units. Amps and seconds are both SI base units, so I don't need to go any further. It's amps seconds. Now I could have used a more complicated equation like potential difference equals work done per unit charge and made charge the subject there, but the problem with this is that work done and potential difference units for those are going to be even more complicated derived. So that's why you should use the simplest equation that gets you directly into the base units as quickly as possible. Okay, second example, let's do Hertz, which is the SI derived unit for frequency. The simplest equation I can use is 1 over time period. So therefore Hertz in units is going to be 1 over seconds. That's per second basically. And that's the easiest way of getting it. Now I could use a different equation, for example, speed over wavelength. Let me show you that one. So that's going to be Hertz is equal to speed, which is meters per second, divided by wavelength, which is meters. And the meters would cancel out to give you per second again. But as you can see, there are sometimes there's an easier version of doing each one. The third example, let's do joules, which is the SI derived unit for energy. Now I could use any equation for energy I wanted, but I would say the easiest one is half mv squared, kinetic energy. Now the half doesn't have a unit, so the joules is going to equal mass, which is kilograms, times speed, but that's being squared. So if I expand that bracket, that becomes kilogram meter squared per second squared. A final challenging example, ohms. Ohms is a SI derived unit for resistance. So I'm going to use Ohm's law to get the equation for resistance, which is potential difference divided by current. Now let's write that in terms of its units. So ohms is equal to volts per amp. Now amps is a SI base unit, so that's fine. However, volts isn't. So I'm going to have to look at another equation for potential difference. So I can use energy per unit charge. Now the issue with that is neither joules or coulombs, which is the units for energy and charge, is an SI base unit. So we're going to have to go even further. So energy we showed in the last example can be written as half mv squared, which is a very quick way to get the units for joules. So in terms of base units, it's kilogram meter squared per second squared. And coulombs can be written as, or charge can be written as current times time, which is amps times seconds. Okay, so now we have kilograms meter squared per second squared divided by amps seconds, and then that whole thing divided by amps. And that simplifies to kilogram meter squared per second to the minus 3 and amps to the minus 2.